Okay, so thanks everybody for coming to this talk. So I will be with Denis Yaroshevskiy presenting this talk about how to deal with SIMD programming in C++20 and trying to introduce novel ideas and tools for doing so. For people following at home, you will be able to grab the slide on this tiny URL link if you want to follow along. Or access to the code and so on. So what is this all about? Let's start this talk a bit like like an elevator pitch. Okay, what I am trying to speak about, what's the context of our work within this SIMD things. Let's say you want to do some computation, like you need to quickly find values in a bunch of bytes, like 1,000 bytes array of either char or short or integer or whatnot, and you want to do it as fast as you can. First, before going fast, let's do it correctly and try to see how fast I can go using a good old standard algorithm find or find if. And you end up with this kind of performance graph. So time is in nanoseconds over there. You have your different types, and as you see, the bigger the type, the best performance comes. So if you look at integers, we got like something like 72 nanoseconds compared to the 240 something for char. But the question is, can I actually do something better? Because maybe the compiler knows how to do this kind of operation. Maybe it can optimize things. The fact is, actually, you can do a lot better. You can do a lot better because currently, if you're using the tools we are going to introduce, you can actually vectorize this find operation, and you end up having a speed up of around 10 for integers, a bit less. Around how much is that? 60 something for short and basically 32 for char. So you can go far more faster. But the question is, it's faster, but is it actually the best we can? Okay, so let's say you actually you try to find zero in this large amount of bytes. Another way to find zero in a bunch of bytes is to actually call sterlen, which is basically this. You are looking for the zero at the end of the string, and then you find it. Sterlen is easily and manually optimized in most of the standard library. And this is the speed of an actual sterlen. It's basically 8 something nanoseconds, which is roughly what we got. So we actually go at the speed of sterlen, except we have a function call that looks like a standard algorithm function call, and it is still optimized. But you may say, yeah, but fine. Actually, you just run over the data. It's trivial. Yeah, okay, let's do something less trivial, like an inclusive scan. Again, you are doing this partial sum over integers. Still, again, 1,000 bytes total volume of data, and we got again this kind of graph where we go from 70 or almost up to 204, 205 for char. And again, you can actually vectorize that using our tools, and you will end up with this kind of graph where basically we go twice faster for int up to how much is that? 4 times faster, a bit less than 4 times faster. So the speed up is less impressive than before because the operation is more complex, but we're still beating the standard code, which means that basically the compiler is doing nothing of those complex operations, and the auto vectorizer just don't work. Okay, but maybe I can actually do even better. What about a very complex operation like remove if? Remove if you look at it from afar, you can say, yeah, it's not something that I can vectorize actually, because you are moving pieces apart to the end of the container, so there is nothing that you can actually do in parallel. Okay, and when you look at the performance for remove if, the interesting part is that you want to plot the performance with respect to the percentage of value you want to actually remove. And what you see is that if you remove nothing or everything, you go faster than if you remove any intermediate percentage, because in the middle of this graph, you are trashing your branch predictor, and every move and if is basically reducing the performance. And the worst case scenario is at exactly 50%, where you got like 25,000 nanoseconds for char down to 1,470 something for if. So let's focus on char. So this shape is basically the effect of the branch predictor, and one way to do that is that if you can actually vectorize it, you will remove the branch, and that's exactly what we do. And we can actually vectorize remove if, which led us to, in the worst case for us, a speed up of 2 and something, okay, or 4 in this case, and for the worst case, we go down from 25,000 down to 1,000, which is a 25 times speed up. And the same will apply with different values, so it's rather 10 or 12 over there, to all the types. The worst case being, of course, int, okay, because we have this less interesting shape there, but we go from roughly 10% win to a 3 times, speed up. So even a free move if you have the proper tools, that's what we want to actually show there, you can actually vectorize those operations. So what I want to speak about this in this talk is how we went there, what kind of operation and tools we put up to do this, and what we can do to go further with this kind of library. So, as you may have guessed already, what we'll be speaking about is Eve, which is our new tool. Eve is C++20, a SIMD library, and maybe some of you need to actually be reminded what SIMD stands for. If you take a regular, normal, ancient CPU, the model you can have of its operation is that you get a stream of instruction, and each instruction will be applied to one value, which is usually stored in a register. The instruction is decoded, it's applied to the data, and you get a result. And every clock cycle, you will get one instruction fed in and one result pushed out. And what is SIMD then? Well, this model is what we call the single instruction, single data model, because we have one stream of instruction with one stream of data producing one stream of output. So M in a SIMD obviously stands for multiple. It's now the single instruction, multiple data model. We still have this single stream of instruction at one point. And on the other side, we are working on multiple data at a time. SIMD computation in general is far more complex than that. What we usually do in regular CPU is that those data blocks are stored into what we call a wide register. It's a register with a fixed size, like 128 bits up to 512 bits. And you fix some amount of data into these large registers. So in this example, we have 4 data in each register. So every clock cycle, you will process one instruction over those 4 data and produce 4 results. The intuition is that if everything else is correct in terms of performance, you should get the speed up, which is roughly around the size of these wide vectors. And the issue is that usually when you want to do this, it's a bit of a mess. First, because you have like a lot of different SIMD systems. If you just look at x86, it's already a lot. It's probably a dozen or more now of variants of the same instruction set with different size, 128, 256, 512, and different level of features and supports. And if you want to cry a bit, you can look at all the operations that are sitting inside AVX512, which is as big as all the others combined. So it's a lot of things to process. And if you get even worse, because other architectures has different instruction set with different supports and different features. Well, so probably what people do usually is that they just pick one architecture because working by hand on multiple of them is very complicated. But even if you say, I would just deal with x86, the question about which version of x86 SIMD I need to use is actually complicated to answer, because if you look at some benchmarks, if you go back to this remove functions, okay, we remember that we have this old scale of versions. We have 3 different x86 versions, 3 different instruction sets, SSE2 there, AVX, and SSE4. And we see that we have different level of optimization and speed up. And it can range from, you see, basically, where is it there? I mean, ×2 to ×4. So it's important to know which one of those instruction sets you want to target. The size, the number of features, and so on and so forth. The reason why SSE2 is behaving strangely compared to the other one is that it lacks some operations that SSE4 and AVX2 provides, and then the change in the performances. Okay, but I'm writing code, and you are telling me that there is a special instruction inside the processor. Maybe somebody already take care of that. Yeah, maybe. Let's see what's already exists. First intuition, we are dealing with special CPU instruction sets. Maybe the compiler can do it. It's like its jobs, you input the code and you get instructions. Most compilers now provides what we call an auto-vectorization pass at high level of optimization. And if your code is simple enough, like it looks like a transform or a transform reduce, and you use classical types like int or float or double, and you don't call fancy function, it will probably do a good job or even a great job. So good. But what if you're not there? I mean, I don't know. Like you want to do the sum of the inverse square root. Well, sucks to be you. It won't get auto-vectorized. Okay, maybe I can actually ask for special treatment. Maybe there is pragmas or special compilers I can use. OpenMP has a pragma SIMD that you can use, and it tries to auto-vectorize by looking at your loop codes. And you have special compiler like ISPC, but again, if you don't fit into the model of the pragma or the compiler's programming model, you're stuck. Okay, but maybe there is something into the standard library. So there is an unsec execution policy in the standard library that is supposed to trigger auto-vectorization, but as we see, it kind of fails. You have other library like HPX that try to fit to fit this gap, fill this gap. But still, again, it's mostly either best effort or quality of implementation of the compiler. Sometimes you are actually happy because someone actually made the specialized tools for exactly your use case. Maybe you are doing, I don't know, JSON parsing, and you can use SIMD JSON that will speed up your JSON parsing things. Maybe you do image processing, and Allied is probably a good things to try. But sometimes you won't find anything, and what's left? Well, you can actually write everything by hand. And to have done it quite a few times, you don't really want to do that. The code is obscure. The function and intrinsic names are completely mind-boggling. And the code, the semantic of the algorithm will be lost under all these architectural operations. So it's not easy. So what we want to do is provide a way to simplify that, or at least make it usable by a regular developer. So enters Eve, the expressive velocity engine, which is, as I say, the C++20 library that wraps all those SIMD nonsense. By doing multiple things, it provides a library of core types that will help you have a regular value semantic types wrapping those registers, and some others like the value registers, the logical registers, and all the helper types you need to make those works. There is a bunch of algorithms in the sense of the standard library. And the interesting part that it's just not just already made algorithms, it's also algorithm building blocks. So if you want to slightly change what the algorithm does from within, you can actually write your own. And we have a lot of numerical functions ranging from simple operators to CMAT-like operation to special function, polynomials, and so on. So you can actually already write complex math with that. We support all these 66 flavors and 64 bits and now 32 bits ARM. And by support, we mean that it's really tested and maintained. We have a partial support, which means the code exists, but the tests are less so precise for PowerPC also. And it's a multi-license, so you are pretty much free to do anything you want with that. Send us a postcard, I will be happy. How does it work? What is actually required? You could actually use any C++20 compliant compilers. We are quite pushing the envelope, so it has to be quite the latest right now. Clean GCC latest version, so it's probably now GCC 11 something and Clean 13, if I'm not mistaken. It will be this way, moving with the latest version up to the point we can actually use modules, which will basically set the things down. There is no to few supports from MSVC right now. We are working on it. MSVC Clang starts to want to cooperate a bit more than the regular MSVC, but it's still a lot of fighting the compiler's inadequacies, but it's something we are thinking about. So how does it look now? Let's say you have this piece of code, so you will use this wide type, which is our main SIMD type wrapper. So this is a wide of floats. You can fill it with floats. So you can either load it from memory, or you can fill it with a constant, or you can fill it with a lambda function that will compute every element in the lane of the registers. Well, you can then, I don't know, like for example, you can print them on the standard output, and you can apply operators on them and call functions. I will go back on that a bit later, and you get things like this. The actual SIMD instruction set used is decided at compile time. There is no runtime dispatch there. We have tools for doing it, but it's not done this way by default, which means that you have to choose which version of the SIMD instruction set you want to compile with, and the result will change. But as you see, there is no trace of the actual architectures anywhere in the code. It's completely agnostic of the size of the wide or the actual support of the architectures for a given function. This we take care of. And so, for example, there we are compiling for SSE 4.2, as we see there. We print the X and Y vectors, and we print the result of this cos things operation. So SSE provides 128 bits register, so we have 4 elements in the register compared to the AVX2 version, which is twice bigger, so we have twice many values in the registers, and the values go forth. You may be curious about this notation. So cos is a function. No, in fact, cos is not a function. Cos in Eve is, like every function, a callable object. And we decided that as they are objects, maybe we can do something fine with it, which is actually to, provide transformation on the object. So quarter circle is what we call a decorator. And we will see what's going on with that right after this. This quarter circle is actually another function that will transform the semantic of cos. Instead of doing cos a given way, it will change either the precision or the speed or the input range of a function. What does quarter circle does? Well, computing a cosinus in SIMD mode is a bit complicated. There is no such thing as vectorized cos, so you need to compute it using math. Basically, we do some polynomial evaluation to approximate the cosinus, and to do so, to do a proper efficient polynomial, you need to reduce the input, because it's a periodic function, so you don't care about cosinus of 10,000s. What you are currently curious about is cosinus of something between, I don't know, some fraction of pi. But if you knew already that all the input you gave to your cosinus function is in a given quadrant of the circle, maybe you can go faster, because maybe you can simplify the reduction function. So the question is, what should cos does? Should it do the complex slow things, the less complex and faster things, or the very fast but very incomplete things? And you cannot choose as a library developer. So what we decided to do is to provide way through the decorators for people to choose the trade-offs they want to pay. So what does quarter circle of cos means? It means that I imbuing the quarter circle range reduction semantic to cos. That means that now this object, quarter circle of cos, is computing the cosine of x only if x is between minus p over 4, p over 4, the first quadrant of the circle. If you are outside that, it will just return none, because it doesn't care. And if you do this, you are actually in what exactly the polynomial expansion of the cosine wants. So we're just computing a polynomial. We have multiply, additions. But maybe you want to do something a bit bigger. Maybe you want to handle anything between pi over 2 and minus pi over 2. So you can use half circles, and we just do that. So the compilation is going on, and you will get a slightly longer code, because we need to do a simple reduction, and then you end up with those MLA polynomial evaluation. And of course, you can ask for full circle, which is a complete between minus p and plus p, and then you get a even larger code, which is a bit slower. Okay, but what happens if I just do that then? Because that's probably what you want to do in the first place. Okay, Well, you will get a quite large cosinus, because what we will be trying to do is look at all your values, try to find if all your values fit into a given quadrant or a couple quadrant. And if they all fit there, we call the fast version of the function. And if not, we will compute every pieces with a larger algorithm, and we will merge the results. So in our case, it's correct, but you have the control over the speed and the precision of what you are doing. Other decorators include stuff like raw or pedantic, that will say, for raw, I want to go as fast as possible and I don't care about the precision I can lose. And pedantic is the other way around. You will compute slower, but with extra accuracy or extra care for corner cases. So that's one interesting features we have. So as I say, Eve is based is built as a C++ 20 library. So let's have a look at what's going on inside. The main features of C++20 we are actually using are twofold. The actual C++20 features, which is concepts on one side, and on the other side, which is more like a 1720 thing, which is if const expert and all the extra features on const expert evaluation. So we use concept to triggers and triage the selection of a given function implementation based on which kind of assembly extension set you are using at the moment. So this apps function will only be picked up if you are compiling for x86. So we already home in on a given implementation. Then we use other concept to say that, okay, I need to get this type to be an actual scalar value and not something else. Okay, so you can actually have, you know that you are dealing with integers or floating points. And once we selected that, inside those functions, what we do is that we take these types, okay, this register type, and we compute something that we call a category that will tell me exactly what kind of elements are inside this register, how many elements, what kind of basic types, and properties like that, that will help us do this if const expert web of selection between, okay, is it an unsigned value? Because if it's unsigned, I don't have anything to do. If it's a special types with a special size that I know about and I have an intrinsic, I will just call it. And if I can't, maybe I have a special formula for larger cases. Sometimes I can't do anything, so I will just call map, which will do every operation piecewise. And sometimes I may have an optimization, but not all the time. Maybe I need to be in a given subset of instructions. So we can actually, if const expert checks that the current instruction set we are using is at least or under this one, and then we can select the proper implementation. And as we see there, we got all the proper optimization possible for this function. And all functions are built this way. Find the proper concept that selects the correct architectures, then use categorize to know which kind of optimization I may be able to do. And this helps us actually be sure that we do the correct thing at each time for each types, each size, each architecture. I will now pass back to Denis that will speak about how and when to use our algorithms.
Yes. Hi, everybody. Okay. With this, we're going slightly faster to talk about the algorithms. At the time of creating the slide deck, this is the algorithms we had, right? We had all of, any of, none of, all kinds of finds, equal, mismatch, transform in place, transform to. So if you look at the standard, right, we only have transform that accepts an output iterator, right? But if we know that we're going to write to the same place we're reading from, we can be slightly more efficient. So this is why we have two versions. Same goes for reduce, inclusive scan in place, inclusive scan to. Same idea as this transform. Just if you are in place, we can do it slightly better. And finally, we have remove if. It has a caveat, and I didn't fix the caveat yet. There are two platforms, like the two platforms I didn't do yet, right? I know how, just didn't finish. Okay, so let's have a look at a first example, like so very basic. We're going to find a negative number in a vector, right? This is how it looks. We call find if, or we pass a vector, we pass a predicate, right? The first thing to note here is, well, hopefully this makes sense, right? But we are passing a vector and not a iterator pair. All of the algorithms that we do are range-based, and the reason is that sometimes a range knows a little bit more about the underlying data than the iterator would. For example, it can know that the underlying data is aligned or something like that. So this is why everything is range-based. And the second thing we can see here is that, yes, we have, well, this is the main loop. We have vector instructions, good stuff. This is actually almost what we showed in the beginning in the benchmarks. There was just finding a 0 and not less than 0. Okay. There was a lot of out on previous slides. Let's put some types in. Right. We return vector const iterator. No surprises here. Internally, we will go to pointers just because we cannot really do SIMD with vector iterators, but then we'll just compute you that type you expect and everything will be all right. The second thing to note here is the types of the predicate, right? We accept a void of int, right? Which, as Joel mentioned, our abstraction on top of a register. So on my machine, this will be 8 integers. Well, why is this interesting? It's interesting because in many SIMD libraries, you will see people trying to use templates to account for both scalar and SIMD code, right? And so you have a cleanup that is in scalar, and you have SIMD code to do the main loop. However, we find it is difficult to write. You need to do, 2 versions of the same function, or you need to do some sort of tricky templates. Instead, we just always accept the SIMD register, and we have a way to deal with the cleanup part that I'll show you at some point. A second thing to note here is that this less returns us not a Boolean, but it returns us a logical of vector of values. So this is equivalent for my machine will be of 8 Boolean values for integers. Yes. Okay. All of the operators are overloaded to work like that. It's maybe you're really opposed to operator overloading, but this is really common for SIMD code. People do it like that, and it works okay. The last thing I'm going to show you here is again this main loop. Right? What do we see here? We see that we load 4 registers and then do some operations between them. Right? The reason we load 4 registers is because the find if will unroll the code for you. Because this is very beneficial to SIMD code to do unrolling. And this is done by the library and not by the compiler. However, it can be a problem if, let's say, your predicate is complicated. So let's say we have some very complicated predicates if we use if or red function, which converts a floating point number into a rational number, like and then you that was rational, but you know what I mean. Like, and it returns you if the denominator is bigger than 7. It's a bit artificial example, but whatever. The point is that this conversion to rational number is expensive. And so as a result, you get a gigantic assembly over here, right? Because we were going to try to unroll it without any actual win. So we can tweak it a little bit. We can say, if I'll go, sorry, let's look at the number of instructions just to remember. So this is what, 700 instructions. Okay, now let's do, if I'll go no aligning, we will not be benefiting in any way from trying to align our accesses. And if I'll go, let's say, unroll 1, right, to disable all unrolling. And as soon as we compile, right, we get to 189, like, which I presume should give you the same speed. Okay. Now, with this, I'm going to assume that we're done with find. Should just make sense, just works. Now let's look at our next algorithm, which is mismatch. If you look at standard mismatch, it is a separate algorithm from find. There is going to be a separate loop that goes over to arrays and compares elements. However, we really want it to be defined because writing just a basic for each loop in SIMD is fairly complicated. This is how we pull it off. Let's say we have two vectors for simplicity of integers, right? And I have two iterators, pointing into one in the first array, one in the second array. I can load the SIMD register from each one of them. It's fine, it will work, but then I have to write a separate loop. So instead of it, we will introduce an abstraction called zip. It is going to represent a special iterator, right? That when loaded, returns you both of these registers in a single object. And then we can just call find on this zip. And actually, we decided to call this object that consists of two registers also a wide, only of tuple of int, because this is int, this is why it's tuple of int. Kumi is our tuple implementation that is like standard but better, right? Why does this make sense? Why does it make sense to call this wide? Well, it behaves a lot like a wide of just a scalar register, just a scalar type, like a wide of int, only with a different scalar type. So I can do equality, works fine. I can move elements around in it as if I move pairs of integers around it, and it works fine. And so a lot of our things just work. It's very nice. Now let's have a look at the interface of Mismatch. Because we have a zip, we have slightly different interfaces than standard ones. This is standard Mismatch. It accepts a range as pair of iterators, a second range as a one iterator, and a predicate with geo equality, and returns you a pair. However, we have a zip iterator, and a zip iterator is a much better abstraction than a pair of two iterators. So we will return a zip iterator. Another thing that, yeah, we are range-based. So we will accept two things that together zip to a range, right? And this is slightly more powerful than just accepting a first, range and then an iterator, because you can pass here an iterator and a range and an iterator, or two ranges, presuming they're the same size. But actually, sometimes it makes also sense to pass in a pre-zipped range, right? So he passes a zip over two ranges. It's called zip range pair, and we just accept a zip range pair and a predicate and return a zip iterator. Now let's see how we can use this to, let's say, run memcp. Right, this is standard memcp. It's an interface to like memcp that looks like standard. You accept two bytes of this size, and you need to compare them as if, say, a uint 8s, and then you return a negative number if the first one is less and the positive number if the second one is less. Okay, so how can we do it? Well, first of all, we're going to convert them to uint 8s, right? Then we're going to use one of our adapters and helpers that we have called as range. So we will create a range of this from the first, from the first range. Then we're going to zip it with the second one, and finally we will just call mismatch, right? This iterator, this is returns as a zip iterator, and as you'd expect, if the zip iterator equals to the end, then we didn't have any mismatches. This is just going to be the ranges are equal, we return the 0, everything works. And here we're going to do the difference, which is will give us the behaviors that we want. If the first one is less, it's going to be negative. If the second one is less, it's going to be positive. However, another interesting thing here is this if read, right? In the standard library, when you want to read the scalar value, use operator star. However, this leads to problems sometimes known with proxy references. And for our library, we don't have to deal with that. We use read and write functions to read scalar values from iterators. So I'm going to use if read, and that will return me a pair of values. Right. And finally, if we look here in the assembly, there's a lot of assembly, but this is the main loop. And it looks remarkably like what you would find in the one of the glibc implementation for one of the platforms. Okay. Now, in that example, we looked at zipping the same types. But what if you want to iterate over ranges of two different types, right? Let's say integers and doubles. Well, it just works. So we can create a wide of int and double, and we'll just use the maximum. So in our case, like for example, on my machine, I can do 4 doubles in one register. And so this will be my limit. So I will use a small register for ints, and it will just work. So fine. Okay, this zip thing is very fundamental to what we do, because it allows us to do to write more complicated things and not just use all algorithms on a single scalar array. We can, for example, do inclusive scan of complex numbers. We have 2 vectors of real parts, of imaginary parts. This is initial value. We define our plus operation, and we can call inclusive scan on the zip. There is an interesting difference here from what the standard inclusive scan will accept, and this is this pair, right? Standard inclusive scan here will just accept the operation. However, due to how SIMD algorithms work, we also need the initial value, not the initial value, sorry, the 0 value, the identity element. And we couldn't figure out a better way to pass it than to use a pair. So if we need an identity element, that algorithm will accept a pair of an operation and an identity element. A second interesting thing here is, well, this is 0, and 0 is magic and special, right? So right now, this is 231 instructions. However, for 0, we can use one of the ifs constants, and we can use if 0, and it should go to, yes, it goes to 211 instructions, which is smaller and more efficient. It is smaller in the proper place. Okay. And with this final example I'm going to show you, because I'm going to give you tutorial, is we're going to write a loop that is from a real product, right? There is this person, Max Demarzi, and he has a database implementation called RageDB. And he wrote me an email at some point asking that he needed to solve the following problem. Like, you have some elements, and you have a predicate, and you want to collect the indexes of all the elements for which the predicate is true. Well, the first thing I did was the same answer you would get from anybody when you ask anything on the internet. How do I do X? Don't do X. Right, this is not maybe the best idea. Here's why. The thing is, okay, like we collect, first of all, indexes are, what's your default index type? Well, it's probably 64-bit, maybe 32-bit if you try hard enough, right? But that limits your parallelism ability, right? I can do only 4 64-bit elements in one register, but I can do 8 of 32-bit ones. The second thing is even more fundamental than that, and it is that if you do basically, okay, you got the indexes. I presume that the indexes do not have semantics in themselves, right? You want to do something with that. But so you would need to collect the data from indexes. But with SIMD, if you want to do that with SIMD, it's not very efficient. Like, SIMD wants the data to be contiguous, and you're just loading the data from multiple places. It's doable, but it's not fast. But however, he needs this to be solved. So let's solve it. And after I wrote him a prototype, he deployed it, and he claims that requests per second went up more than 5 times. Let's see how we can do it. The fundamental building block to implementing this operation is called Compressor. You take a register, you take a mask, and you take a pointer. And then you write all of the elements that are selected in the mask together and return where did you stop. Right, this is a new pointer. Like it's like a remove if only for one register effect. Now, it has this decorator called unsafe. This unsafe allows me to write a little bit of garbage on the end, like it's up to the register size. This allows the separation to be actually efficient. Okay. Let's have a look now how we can use this to build this operation, right? This is a function, collect indexes. We accept a relaxed range. Relaxed range is our range concept. It accepts any standard contiguous range, like vector. It also allows you to do things like return aligned pointer, for example, from a begin. There's a lot of customizations, all that stuff. There's a predicate. And there is a vector of output indexes. The reason I'm using an output parameter is A, I don't want to deal with allocators, and you can just pass me an allocator. And B, it's a very natural way to pass me as index type. And as I mentioned, if you have a smaller index type, this will be more efficient because you can do more parallelism. Okay. First we're going to assert, that any element in the register can fit into the index type. Clear. Do the check that the range is not empty. In many other scalar algorithms, right, when you write this is a cosmetic check or is a preference check, but unfortunately for us, it is actually a functional check. For example, because we will do a memcpi sometimes, and your begin and end might be null, and it's not legal to do a memcpi from a null. Things like that. Okay. Now we're going to use one of our components to convert from the range that we got, this is relaxed range, to actually range we can do things with. It will strip vector iterators and all of that stuff to pointers. And here we're going to pass consider types index type so that we we're going to select how many elements we're going to do in one go. And if, let's say, your range is chars, then you can do, let's say, 32 of those, but you don't want to do 32 index types, trying to do them like in registers. It's not going to be efficient. So you want to consider that and select a maybe smaller number of elements per iteration. Okay, to be honest, at this point, I would usually just call for each and be done, but I'm not going to. Instead, we're going to unpack that. So we're going to get the more advanced iterators. We're going to compute how many complete registers we can fit in up to the end. We're not going to do any aligning or anything because the operation is very complicated. It's not going to be beneficial. We're going to over allocate the output a little bit so that we can always use unsafe store and we're never going to run out of space. Now, this is our index that we're going to store. Like, imagine if you were writing this in scalar, you would have something like, for I equals 0, I not equal size plus I. Well, in SIMD, we are not going to use just one I, but we are going to use n of them, let's say 4. So we're going to do, on first iteration, we're going to do 0, 1, 2, 3, plus 4, or 4, 5, 6, 7, plus 4. That kind of stuff. So this is our wide I instead of I. And on every iteration, we increment it. Right. This is the main kind of operation. So we load, we apply the predicate, and then we do compress store of indexes. Perfect. Now there is a little bit on the end. Let's say we had, we were divisible by 4 all the way, and we had 3 elements in the end. It's going to look, well, the modifications we need to do here are first this load with, instead of just doing load, we're going to do load with ignore, right? We're going to keep first 3 elements. This is effectively will do a masked load. So the first 3 elements will be okay. And the last element must be garbage, right? There's no guarantees to what it is. Then we, apply the predicate. We need to clean out, we applied the predicate to garbage. It might be true, it might be false. We want to clean it out, right? So this is how we clean out that garbage element. And then finally, we do, again, unsafe compress store because we over-allocated. We know we're going to do this. Finally, we're just going to, resize and shrink to fit and return the result. This is a code that is deployed and is more than 5 times faster. And if you look here, it does the SIMD thing. So it loads some masks that we have prepared, it does a permutation, and does a store. Okay, and with this, I'm going to give you back to Joel. I hope not everything falls apart.
And I'm back. Apparently, oh, it's still working, so that's great. So yeah, let's go back to something we saw earlier, which is this inclusive scan over complex numbers. We saw that we could actually, like got those vectors or floats, use zip, write a proper plus, and so on. And what is actually not very interesting as the users is to have to deal with this get things to get the PCs from the complex and so on. So it would be cool if we could actually have something a bit more user-friendly for dealing with vectorization of code over structures instead of just arrays of simple values. So what we do is we actually provide something that lets you write complex-like structures with support for vectorization. So we have these struct support helpers that you can inherit from your types. And they say, okay, this is my type, CMPLX. It's basically a float and a float. And this will generate all the required threads and overloads for being interoperable with Eve inside. This is the easiest way to do it. We have an external way to do it, which is much more complicated because you have to manually specialize a bunch of threads. But if you want to adapt existing types you cannot touch, it is also possible. But let's focus on this one. So we write complex as a structure made of two floats, and we write those small ADL-based accessor, re and m, that will wrap the get 0 and the get 1, and will let you access the value of the real and imaginary part. And as we want complex to be able to work in both scalar and SIMD mode, the type you wait there as an input, it's not the CMPLX, it's something that models the like CMPLX concept. That means that anything that is either CMPLX or a wide of CMPLX. So it can catch both the SIMD and the scalar way of doing things. And once we have this CMPLX function, you can actually manage a bunch of operators. First, you have an opt-out to remove ordering operation. So we don't want to have less than and so on complex because it doesn't make any sense. So you can disable ordering right there. And we will be reconstructing most of the operators in a slightly boost operator way by requiring compound operators to be provided, from which we will build all the other variants of the operators. So plus equal give you plus with complex, wide of complex, and so on. So you can just write it using this accessor we wrote a bunch before. You can have unary operation like unary minus, and then you can have minus equal. It's important to note that we don't generate minus from plus and unary minus because it may mask some optimization opportunities. So you really have to be exhaustive on your operators. So we get plus, we get minus, you can get all the other one. And as soon as you put it, it's available outside. You can also stream your structures quite trivially. And as soon as you have that, you are also able to print an instance of wide of CMPLX. So we reconstruct everything from this sample of operators overloads. But sometimes what you want to do is to actually change the behavior of an existing Eve function. I want to compute the absolute value of a complex. It's basically computing the square root of real square plus im square. And I really, really want to be able to call ev apps over my complex structure. So we have this tag dispatch mechanism that lets you say, okay, for this function, apps, so every function object in Eve has a tag associated to it, so you can actually refer to it in an overload. Whenever I call Eve apps on something that looks like a complex, I do something with it and return a result. And now you could actually you are able to call Eve apps on the CMPLX. Fine. So you could actually write structures and imbue it with vectorization at the function level. But we can do better because we also have these SOA vectors that can take any kind of this adapted structures, and it will act like what it says on the box. It's a vector, but stored in a structural throwaway way, so it's very amenable to vectorization. And SOA vector is also recognized as a range for our algorithms, and it overloads the key elements of the range protocol we use. So you could actually just pass it directly to inclusive scan in place without having to write everything else. And by default, we use plus, so we don't have to specify the operation, and because the plus is already specified and defined on the structure itself. And what happens to the code? Well, the code is better because SOA vectors know a lot about what it does in terms that it knows that it's properly aligned for whatever kind of SIMD instruction set you want. It knows how it behaves with respect to range, and you know how many elements it has to manipulate. And if we look at the main loop, we have got this very tight computation on the inclusive scan thing. So you got the add, you got the shuffle, and so on, and everything is rather tight. So you can actually write, and that's also something we are actually probably most proud of, is that you could actually get code with arbitrary structures getting vectorized through our high-level algorithms. So let's do something else. Let's say you want to do some basic physics. You have a bunch of balls and they bounce on the floor. So you want to do some small scale physics simulation, like tracking the position and the speed of your ball as a float. And every ball has an elasticity factors as or where it can bounce, And we have an integral there, so we can actually mismatch types inside the structures. That's not a problem. That count how many times you bounce, because once you bounce a given times, you don't care about the ball anymore. So that's the structures with the classical way of getting the accesses to the elements. We don't do anything fancy because we don't need special operators. And what we will be doing is writing a small function object that say, when you give me a ball, I will compute the physics on it. So I will compute in falling. I will update the position of a falling ball by applying some, physics, multiplying the time step by the speed and so on. I will update the speed by using the gravity constant and so forth. I will also compute a state for whenever a ball is actually bouncing by reversing the speed and multiplying by the elasticity of the given ball and counting that I bounced. And the question is why I am doing both, because when you are doing physics, you need to know, you can test, you can do an if, but you cannot do if in SIMD. So you have to compute both states and select them using if else at the end. And we say that if our position is very, very low, we are going to bounce, okay? And if not, you keep falling. And when you want to run your simulation, you just call transform in place on that. And let's say we unroll by a factor of 2. And whenever it's done, we can use a good old erase remove if items to remove all the balls from which the count, the bouncing count is actually greater or equal than the max bound. And that's all we do. So the code looks actually like an actual code that do something. It's not a bunch of intrinsics, wedging walls. And we get something that is actually, again, sorry for that. Let's go to the main loop, something which is very compact. So we got the comparison, we got the blend, and we got all the updates over there, and so on and so forth. Okay, fine. So algorithms, functions over classical registers. We have the support for structured code and structured operation. So now what if you want to start using it? Well, some practical points. What about bugs? Oh, well, probably we have a bunch of them, okay. And we are working on that. We have an extensive set of unit tests. We are not immune to code gen issues, but we try to make them as few as possible. So if you try the library and you find something, just ping us. What about ABI and API stability? ABI stability, we don't care. We'll explain that a bit later. And as for API stability, currently, nope. We are still crashing through writing the code. We are still finding better way to express some things with a lot of optimization opportunities. So, well, we are still breaking things. We started releasing a tag version so you can keep track of what is going on if you really want to. But except for the very core things, we are still playing with a bunch of API. So what if you still want to use us? Well, this is a recommended workflow. We strongly advise on focusing on the critical components in terms of performances. You are not going to vectorize your apps. You are going to vectorize a bunch of very critical function/loop nests. So focus on those. Extract them as some kind of a standalone library of computation or so on that you can actually test and compile somehow. And you can use either dynamic linking or multiple static linking if you want to support multiple architectures in a single executable. Eve provides a compile time way to know what you are compiling for. That's the current API we see in a bunch of slides. But we also have a dynamic test that lets you say, okay, am I runtime running on a machine with this or that supports? And then you can actually select the version of the function you want to call. Every calls in Eve is actually resolved at compile time, so you will need to compile for multiple architectures yourself. And if everything fails, just contact us. It will be a pleasure to help you design or debug whatever you have. There is, of course, a lot of similar libraries. We probably didn't invent the things. You have a bunch of intrinsic wrappers. I'm probably missing some, but that's the most prominent. So you have VC, which is stated for standardization if everything goes well. You have SIMD and TSIMD, and probably half a dozen of other insert a random consonant SIMD library out there. There is iWay from Google and stuff like that. They mostly all navigate around wrapping the intrinsics, easing the way you use them into regular code. But as best as we know, none of those provide neither algorithm nor structured vectorization supports. And if you really want to dig a bit in another direction, you have you have SIMD everywhere, which is basically rewriting every intrinsics of a given architecture using all the other ones. So you can actually copy past SSC2 code into an ARM version of something, and it will just compile. But so it's even lower level because we don't have any abstraction on top of that. So they are pretty much based on similar premises, and they work quite well for whatever the limited scope they are providing. Some special mention before we close there. Special mention to Jean-Thierry Lapreste, which is our third co-author for the library. It's a guy in charge of the math. And he do maths quite a lot and quite well. So we have to thank him for a lot of our non-trivial math algorithm in the library. A bunch of friends shout out to a lot of people over Stack Overflows in random orders, Peter Cordes, Zibozon, Stephen Cannon, Akrit, that helped us or push us into the right direction for a bunch of our work on the algorithms mainly. And if you ever have an issue with x86, just look for Peter Cordes answers. This guy is a gold mine. We kind of get influenced by Unity for the SOA vector. That's something they have in their own implementation of their system. Dennis made another talk about using Eve quite a while ago now at this exact same conference. So if you want to get more into the gritty detail, you can have a look at that. And we are pretty much easy to find. You can get the slide, as I said already. You can get to and find the library and try it out if you want. We have a Discord for the library, and we are also present on the hashtag include Discord and on CPP Slack. or you can fire us an email or get us on Twitter if you want to bother us with your issues. Thanks again for your cooperation. I think that, Denis, you can come back and we can see and answer a bunch of questions.
We have 1 minute to answer all the questions.
I can do that. I think the most important one.
Oh, we have 5 minutes.
Oh, 5 minutes. That's
5 minutes will do everything.
I think we can answer them like I think a bunch of them are kind of already answered, but we can get to
well, let's get them on tape. Like I just answered.
Yeah, sure. But that's what I wanted to say. So let's start with the mismatch on non-multiple. Maybe you can get ahead of that.
Okay. So I showed ignore. All right. The idea is that when we're doing like we will so mismatch calls find, right? So it's the same answer as for find. As to how it's done, and basically you will load an elements. There will be some garbage on the end, right? And then we will just ignore the garbage. I don't know if it makes sense, but inside you get so the person who asks knows about SIMD. So inside you get move mask, which is bits for everyone, and we will clear the bits for the ones that do not matter.
Okay.
The dynamic thing. Can you answer the last one? Okay, like
yeah, the last one I will do that. Yeah. So how do we deal with the vex evex code generation? We just don't. I mean, we just ask you to put the proper flags in your compilation. I don't know if I can actually. Okay, let me try something.
I don't know what's vex evex. What's it?
Oh yeah, there is two. Let me share something else. There is two way to encode SIMD instruction set depending on the microarchitectures on your x86 systems. And basically, when you switch between the VEX and EVEX systems, you need to use those ugly V0 upper and X start things. So the system knows it has to clear up the high parts of the YMM registers because if not, you will get issues because on some microarchitectures, the large AVX registers are actually shared with the smaller SSC1. The thing is that as we require the actual architectures to be specified there, I don't know if my okay it's on. So as we require you to actually specify the system there. What happens is that I'm compiling code for AVX2 there, obviously. But what I did is I wrote a small function that takes a register of 4 floats, which is obviously SSC registers. And in this case, as we see, we got the V whatever version of the Invent6. Okay, and in this one, I try to basically mix them up. So I'm taking in an AVX register. So this is a YMM something. And what I do, I call this slice member that get me the internal smaller XMM registers. That and in this function, I call the other one, and then I call myself on the YMM, and we basically get nothing because for when we compile, and that's what we saw into the if context of things, we know that we generate all the code with the proper modulation of the version of the encoding. If you compile into separate files because you want to actually call different things with a different setup, then in this case you may have you may need to call 0 upper and stuff, but we let that to the compiler, and usually it's the best way to do that. So if you write code like this, you don't have to take care of that. It's basically for the compiler, it will just generate the correct things. It's a bit more complicated in other situation, but usually, well, either you work with a full SSC register set, or you will be working with the AVX mode anyway. And whenever you have to treat XMM, it will be just emitting the proper version of the Invent6. What do we have next? Yes, so it goes well. Yeah, we select the SIMD instruction set at compile time because if not, we will probably have no performances. And as I say, we have a way to select or discover, let's say, at runtime, which is actually the architectures you are running the code on. And in these cases, what we expect people to do is to actually have this multiple version of the function precompiled and load either dynamically or called directly, depending on this runtime if. We have an example. We have written some example of that for someone, and I think we still need to put it into the actual example folder. It's not that complicated. It's probably more, CMake hackery than anything else. So we'll probably drop an example for that in the repo, if soonish, let's say.
Yeah. Just add that, like this is just the whole format of like we have small components doesn't allow you to do dynamic dispensing small components. On the algorithm level, yes, but we don't do that.
Okay, thanks, Joel. Thanks, Dennis. Thanks for this very great talk. And maybe if there are another questions, maybe they'll find you in the launch, hopefully.
So thanks everybody for coming.
Thanks everybody. See you.